Hello. Okay. It is 2 p.m., so I am going to start. If you didn't see this on Twitter, basically this is a room I created for TryHackMe called Buffer Overflow Prep. It used to be called oscp Buffer Overflow Prep, but for various reasons, it is now called just Buffer Overflow Prep. But if you are doing OSCP, you can basically practice basic stack-based buffer overflows in this room. Now, I just want to preface this by saying that I am no means an expert in buffer overflows. My first experience with them was when I was doing the OSCP, not last year, but the year before. And so most of this is just based off, the standard stack-based buffer overflow. There's no real complexity to it. So you can join this room for free. It's like you don't even have to have a pay subscription to TryHackMe. It's completely free. Quite a few people have joined it already. So yeah. Now I have connected to the VPN. I've got an IP address already, so that's great. The other thing I would note, so the first task tries to walk you through exploiting. The second task, actually, this one tries to walk you through exploiting the Overflow 1. And for the most part, it's pretty detailed. If you do, however, need some more detail, this is one of my repositories on GitHub. Pentest cheat sheets. This is basically a cheat sheet I started writing during my OCP, and I kind of continued it a little bit. So there's if you go to the main repo, then exploits, then buffer overflows, you should find it. But it's basically a whole walkthrough on how to set up Immunity, configure Mona, and it has these example Python scripts which you can use. These should be, I believe, compatible with Python 2 and 3, but obviously you should be using Python 3 these days. So there's a lot of information here, but most of this I have managed to put into these tasks here. So what we're going to do, I've deployed the VM, and I'm going to copy this string, and hopefully it's going to connect. Hey, Mojo's in. That's great. So, oh, look, it didn't connect. Great. Am I connected to... I am. Let's try it again. So, for anyone who doesn't know, and I'm assuming this is the same Mojo, but Mojo helped me write the binary that we're going to be using today. It's a modified version of Vuln server, and it has 10 buffer overflows in it. They each have different EIP offsets and different sets of bad chars, because when I was practicing for OSCP buffer overflows, the only ones I could find had 00 or 0A and 0D. So it was kind of annoying because, you want to practice finding bad chars. That's kind of a big thing. So Mojo helped me rewrite Vuln server to introduce a bunch of new bad chars, which is great. Okay, so we've connected to the RDP. Once you connect, it should pop up this window. Just click Home Network. That tends to be the best one to choose. All right. Sorry about that. Yeah, for some reason, I don't blame TryHackMe at all. It's probably a connection thing on my end, but it's been dropping VPNs like crazy. So we're just going to use my local copy of this. So luckily that means I can at least put it there. So we're going to do this again. Okay, so we're going to go open and desktop and scroll down vulnerable apps, oscp. Okay, I'm going to click play this time. So let's try. So someone said font 6 is big. Yeah, okay, we'll do font 6. Font 6. Oh, font all. Hey, I could just do that. There we go. All right. So we have Immunity running over here. So the only trouble with this is obviously this is full screen, so I'm going to have to go to my other screen to switch, but I apologize for that. At least we have everything running. So I clicked play, and this window pops up, and it says, you know, starting OSCP vol server, listening on port 1337. So I believe the IP address for this box is 130, but I'm just going to double check. Yeah, okay. So now if we do nc 192.168.1.130.1337, it says welcome to the OSCP vulnerable server, enter help, so we'll enter help. And it will show you, these are all the valid commands. There is a bug in the exit doesn't actually work, so I'm going to fix that. But all of these should, and the way they work is you type the command, you do a space, and then you put the value that you want to enter. So we'll just try that. So we'll go overflow 1 space test, and it'll say overflow 1 complete. Okay, and that's how it works. So it's pretty simple. The overflow you want to be doing is here. So basically it's the value that we're overflowing. You got to make sure you have a space though, because if you just do overflow 1 test, it's going to respond unknown command. And the reason I highlight this is because like half the messages I get on Discord and Twitter are people saying, why isn't my code working? And it's just because they missed a space, and that's it. Okay, so we're going to disconnect from that. So that was basically walking through this thing. The next thing we're going to do is we're going to configure Mona. I really probably should have done this before I uploaded the box, so maybe when I fix it I will do that. But all this is basically going to do, I'm hoping copy and paste is going to work, and it's not. Great. So I'm going to give Mona config -set working folder c/Mona/ and then this is %p, and %p will get replaced by the program name, so in this case OSCP. And what will happen there is you'll get this lovely log window, and it'll basically say, yeah, it's done, it's set the working folder. That's great. So you can switch back to the CPU, and everything's still running. So now what we're going to do is move on to the fuzzing. So you can copy this. If you wait for the box to deploy and the IP address to show here, then the IP will automatically be filled. Of course, for me, I'm going to have to change this because it's running locally now, right? So, but luckily, or hopefully for you, it should be fine. So I am going to create fuzzer.py, and I'm going to paste. I probably need to set the paste. Yep, there we go. And then I'm going to change this IP to 130, and I'm going to save that. And so then we just need to run the script. So Python fuzzer.py, and it cannot connect. Why can't it connect? Now, that's probably, there's got to be, I'm gonna reopen it again. The other great thing about this is if you have opened it already, you can just go down to File and click that, and then run it again. Okay, let's hopefully this is going to work. Yeah, of course it's not. That is my IP address. I can ping it as well. I mean, I connected to it, right? Like, let's try that. And it's okay. Okay. So now this is the problem with the script, clearly. 1337. Let's just try that script again. Well, this stream might be very short. Anyone in the comments, if you can see the dumb thing that I'm doing, I would appreciate it being pointed out, because I have no idea. The IP is correct. The port is 1337. I'm going to, I guess, try without Python 3. Oh, okay. So apparently it's not compatible with Python 3 for some reason. I'm going to have to research that, because this script should be compatible with Python 3. All right. Anyway, it's off. It's fuzzing. I will definitely fix that. Okay, so basically what Fuzzer does is it generates increasingly large buffers of A's. So it'll start with a buffer of 100, 200, and it'll go up all the way to 3,000. So if it stops before 3,000 bytes have been sent, like this, and it says cannot connect, you got a pretty good indication that, you know, something's happened at least. So I'm going to switch back here, and we can exit out. And we see, firstly, access violation when executing 41, 41, 41, 41. And 41 is effectively the ASCII code, really, for the letter A. So if you look at the EIP register, you'll see that it's been completely overwritten. So that's effectively what buffer overflow is, right? So the buffer that we sent has completely overflowed wherever it was in memory, and it's overwritten the EIP. And we can also see it's also overwritten EBP and EBX. And in the EAX register, there's, you know, the call command, and in ESP, there's also some A's here as well. Okay, so we have successfully overflowed, right? And this is what it will say here, you know. So that's great. We know that the buffer works, at least, or the buffer overflow works. So now we need to find out exactly where in that string of A's it's overflowing EIP, because we want to control EIP. EIP is going to point to the next instruction, and so if we can control EIP, we can basically, you know, tell it to jump anywhere in our code. So we're going to create another file, and this is just going to be called exploit.py. Set paste again. Okay, and again I'm going to change the IP. So this is a custom script that I wrote. It's pretty good. It'll apply in a lot of situations with simple buffer overflows. You have a prefix, which in this case is just, you know, the command that triggers it. So overflow 1 with a space. It has an offset, which we'll talk about in a minute. The overflow, which is the letter A multiplied by the offset. So in Python, if you have an offset of like 10, then this will just generate a string of 10 A's. RETN is going to be the return address that we want to jump to. The only reason it's not called return is because that's a special function name, not function name, but it's a special string in Python. And if I use that, it would just, you know, not work at all. And then you have padding. So if you want to pad before the payload, which is good if you're encoding a payload, the payload needs some space and memory to decode. And finally the payload, and then I just included this just in case, like a postfix. Sometimes you'll be buffer overflowing in the middle of a command, or it has extra options it needs on the end. So that's always good to have as well. But other than that, it's mostly the same. So it builds a buffer using those variables, and then it'll just send it. How are we going to find where the EIP overflows? And we can do this using a Metasploit Ruby script called pattern create. So currently we send 2000 A's, and we know at some point in that 2000 A's it's going to overwrite EIP. But obviously when you have 2000 A's, they're all the same letter. So what we want to do is get a string that contains a lot of different characters, but in a way that we can know by looking at the characters that overwrite EIP exactly where in the string they're found. If that sounds a little complicated, then don't worry, stay tuned. It's going to become really obvious in a minute. So we're going to use this script, and you give it a -L. And then generally what I do is I take the bytes that crashed and I add 400. And the reason I do that is because we know that it's going to, it's somewhere between 1900 and 2000 the crash is occurring, but we also need bytes after that because the payload that we're going to generate and put in memory is going to be after that. So I tend to play it safe and say, okay, we'll leave 400 at least bytes for that payload. And so what this has generated, it's generated a really weird looking string, but it starts, it goes capital A, lowercase a, 0, capital A, lowercase a, 1, and you see it iterates, right? So it goes all the way up through to A9, and then it goes A, B0, A, B1. So this is, I believe, known as a cyclic string, because effectively it's 3 characters that are basically cycling through different versions, almost like a brute force, right? And so what we're going to do is we're going to copy this, and we're going to go into exploit.py, and we're just going to put it into our payload. Okay, so for the moment everything is set to 0 or blank, right? This string will not exist. It will be an empty string because you're timesing a, you're multiplying a by 0. And so we'll save this, and then I'm going to go back to the buffer, back to Immunity Debugger. I'm going to reopen this because this is crashed, so this won't be able to connect to it anymore. And I'm going to press play, and then we're going to run the exploit code again. Sent the evil buffer, done. We'll go back to this, and it says, okay, yeah, so access violation. Now it's not when executing 6F43396E. And if you remember, there's only 3 characters that are being iterated, right? So it goes AM5, AM6. So actually the first character here and the 4th character here, you can see they're separated by only 1 number, basically. So it goes 6F6E. So that's a pretty good indication that that cyclic string is in memory now. Now, what a lot of people will do now is they'll take that EIP, they'll take this value here, and they'll use pattern, I think it's pattern offset or pattern search or something. There's another Metasploit module that you can use, and it will tell you exactly the offset. But we're not going to do that. We're going to use Mona. And so what I'm going to do here is use this Mona find MSP with a distance. So again, unfortunately I can't copy for some reason, but what we're going to do is we're going to just type it Mona find MSP distance. And again, we're going to use the same distance that we did before. So that was 2,400. And I'm going to try and change this appearance to font 6 again. And hopefully everyone can read that. So it's basically looking for cyclic pattern in memory, and it starts at EIP and it looks backwards along the memory and forwards by 2,400 bytes. And it says, okay, it's found the pattern, and it's found a length of 2,400 bytes, which is great. And then it's examining the registers. It says EIP contains the normal pattern at offset 1978. But then it says, and this is what the Metasploit offset tool won't find, is it'll actually tell you if any other registers will contain this. So ESP points to the offset 1982, and it has a length of 418. So if you think about that, that means that the EIP register starts at offset 1978, and ESP is pointing to memory at offset 1982, which is 4 bytes later, which makes sense because EIP is 4 bytes, and then immediately afterwards, that's where ESP is pointing to. ESP is not being overwritten by it, it's pointing to that offset. And what it also says is that the remaining string that ESP is pointing to is 418 bytes long, which is great because that's enough for most of the payloads that we would ever want to use, really. And then we can ignore EBP and EBX. We don't need those. So that's good. So now we actually can answer this question. So what is the EIP offset of overflow 1? And it is 1978. And submit that, and we get a correct answer. Okay, so now we can actually modify our exploit code, and we can put this offset in here. We can say it's 1978, and we can delete this payload. Okay, and I'll just set it back to an empty string there. So next thing we want to do is find bad characters. Now, a lot of people get a bit confused over bad characters. And again, I'm by no means an expert, but effectively what bad characters are, they're characters which during initial processing of the string by the server or the app, when the app detects these bad characters, it modifies the buffer in some way, or it causes the buffer to end early. So a good example of this is the null byte character, or just 00. In C and C++, if a string contains that character, that's effectively the internal way of telling the code that that's the end of the string. And so it won't copy anything after that string. It'll basically end it. So if your shellcode has a null byte in it, like say it's in the middle of your shellcode, then what's going to happen is only half your shellcode is actually going to end up in memory. But there are other bytes that could possibly be bad chars. Common ones are 0A and 0D, sometimes separately, but a lot of the time if they're together. And the reason for that is, especially in Windows, those two bytes, when put together, are effectively what a new line is. In Linux, I think it's just 0A. It's either 0A or 0D. I forget which one. But realistically, there could be any character that's a bad char, right? Because it really depends on what the application is doing. Now, in these examples, I've chosen some really weird bad chars. You're probably not going to find them anywhere else. But they were chosen just to make it like a challenge, right? To find all of the bad characters and not just assume it's 0, 0, 0A and 0D. So there's another Python script here. First thing we're going to do is we're going to generate a string which contains all the possible characters from 0, 1 to FF. Okay, and we exclude 0, 0 by default because it's always going to be bad. So I'm just going to create a script called badchars.py. And we'll paste that in. And oops, if I generate it, it's going to give me in this byte format, so from x01 all the way to xff. So I'm going to copy this, and we're going to go back and modify our exploit again, and we're going to put it in the payload again. Okay, and the other thing we're going to do, because now we know that the A's go all the way up to the EIP, but they don't actually fill EIP, we're going to put 4 B's in there. So that should completely overwrite EIP with B's. And then we're going to save that. And obviously what we have to do again is restart the app. So we're going to restart it, press play. And then what we're going to do is we're going to run exploit.py again. And I believe it should have crashed. Yep, so now we get access violation when executing 42424242. So that's B's, right? It's 1 higher than the A's, which are 41. So that's great, we've crashed it, and now all of our bad chars string is going to be loaded into the ESP register, because that was exactly what came after EIP, right? ESP points to the bytes directly after ESP. So what we can do, we can right click on the ESP register and we can say follow in dump. And if we look, we see we've got 0, 1, 0, 2, 0, 3, 0, 3, 0, 4, 0, 5, 0, 6, 0A, 0D. So that's interesting. That means that 0, 7 seems to have been replaced by a 0A, and 0, 8 seems to have been replaced by a 0D. So maybe those are bad chars. Definitely one of them is, and that's the thing to remember with bad chars. Technically speaking, if you want to be thorough about this, you should really remove the first bad char and just assume that everything else is fine, and just repeat that step until you find everything. Because bad characters can sort of cause issues further along. So in this case, what's happened is like 0.7 could have been written over by 2 bytes, and that second byte has basically overflowed into the 0.8. But realistically, anything could happen, right? So if there's a program that finds a byte in a string in memory and decides I'm going to overwrite that with the word hello, then there's only one place for those bytes to go, and it's after the bad character, right? So again, not technically realistic, but that's why sometimes bad chars aren't bad chars. And that's what I effectively wrote. Hang on, I'm trying to switch back. So I effectively wrote here, not all of these might be bad chars, right? But that's the way to do it manually, to find them, is to effectively crash the program and look through until you find, a thing that doesn't look right, and okay, then you remove the 0.7, recrash the app, find the next one. In this case, and for all of these in the actual exploit that I wrote, they all sort of fill out at the same time. So we have 0.7 here, but if you scroll down a little further, you see 2E has also changed. And I think if you scroll down, there's some other ones. But this is a very manual way of doing it, and there is a really nice way using Mona. So what we're going to do is we're going to use 2 Mona commands. One's going to generate a byte array, and this byte array is exactly what we generated here, right? It's just all the bytes from 0.1 to FF, because it excludes the null byte, and it writes them to a file called bytearray.bin, and it writes the actual raw bytes. So it's not going to be in this format, it's going to actually be the bytes 0.1 all the way through FF. So if you open the file, it's going to look weird. But we'll do that now. So what I'm going to do, and again, for some reason I cannot copy, so and apparently Control A does not work either. Mona byte array. So the B argument effectively defines the characters that are bad that we don't want to generate. So in this case, it's going to be just the null character. And you see it does a few things. So it's preparing the output. It says it wrote 255 bytes to the file bytearray.txt, which is this string. So what we actually want is the binary output, which is saved to bytearray.bin. Okay. And then what we're going to do, we're going to go back to the CPU, and this is crashed still, and everything is still in memory, so follow in dump. And so what we want to do is compare everything that the ESP register is pointing at with the file contents we just generated. And so we can do that with this Mona compare command. Okay, so I'm going to write it here. So Mona compare -f, and then the path to that file, which if you set up Mona correctly should be in the Mona directory, oscp byte array.bin. And then you set an address, -a, and the address is going to be this address here of ESP. So I'm going to copy selection and paste it, and then I'm going to press enter. And we see in this very small window, which I'm going to make larger and also change the appearance. Okay, so we see we got a corruption after 6 bytes, which is what we expected because 07 is technically, I think, the 6th one. So it's found the bad character 00, obviously, because we left it out. 07, 08, 2E, 2F, A0, and A1. But again, some of these might not be bad characters. The 07 might have caused the memory behind it to change. Technically, it's even possible if this bad character is being processed weirdly, it could have caused all of these, right? There's no rule that says that, you know, a bad character only causes itself to sort of get overwritten or something. But in terms of OSCP and basic overflows, generally it overwrites itself. It might overwrite the byte afterwards. But we can definitely check. And so how we're going to check is we're going to regenerate our string in our exploit code, and we're just going to remove the 07. We're going to leave everything else. And then we're going to regenerate this byte array, again removing the 07. We're going to crash the app again. So actually I might do that first. So if I go down to this byte array command again, and I'm going to remove 07, I'll press enter, and now you see the string it's generated goes from 05, 06 directly to 08. Okay, and I'm going to relaunch the app. And then I'm going to modify the exploit code, and we're going to go along here and we're going to remove 07 and obviously the \x, and then we're just going to recrash it. So if I go here again we get an access violation. Now we need to rerun the compare command, but remember it's entirely possible that this address has changed, so generally I always copy it again. And so we'll copy this, and then we'll paste. Okay, so again, let me change the appearance. Okay, so now this time you see 00 has been detected, 07 obviously because we removed it, but 08's disappeared. So 08 wasn't actually a bad char. But it looks like 2E, 2F, A0, and A1 are all still in there. So if we go back to the CPU window and I go and follow this in dump, we can manually confirm that. So now it goes 0608. So it does look like 07 was just causing the 08 byte to change. So maybe that happens with the rest, and we can make that assumption, and we can say, okay, so we're going to remove the other two. So what we'll do is we'll remove 2E, and we'll remove A0. So we'll do that now. So 2E, and we're going to remove X A0. So that's regenerating the byte array in Mona, and we're going to, actually I should restart the executable, press play. Okay, and then what we'll do there, completely forgotten which bytes it was now. 2E and A0. So I'm going to search for 2E, and we're going to remove that. And I'm going to search for A0, and we're going to remove that. And then we're going to recrash. Okay, so we get an exception. And now we're going to do one more compare, hopefully. Again, I'm not going to assume that this hasn't changed. And unmodified. When you get unmodified as the status result, it means that the byte array we generated matches exactly the bytes that the address is pointing to. Okay, which effectively means there are no more bad chars. We found them all. All right, so we have a nice list of bad chars. And now what we can do is we can answer that question. I'm just trying to find it, right? So if I go back to TryHackMe, one of the questions for each of these tasks is in byte order. So basically, in integer order, if these were numbers, what were the bad chars? So we know that 00 was, we know that 07 was, and then it was 2E and A0. So 2E and A0. And we submit that and we get your answer's correct. So that's great. So we found the bad characters now. So that was, how to do it using Mona, which I did in the exam, in the OCP exam, and you should definitely, if you're having trouble with bad characters, it's definitely a nice way to do it. Technically speaking, when we removed 07 and reran it, and then I removed the other two, you should really do it one by one. So we should really have removed 2E and then recrashed it, and then seen that A0 was the only one left. So really that's how you should do it technically, if you want to be thorough. But I'm pretty sure you can get away with just saying, okay, it's probably these three, let's remove them and try. So now we know what bad characters there are, so we can find a jump point. And the reason we had to do this first is because sometimes jump points contain bad characters, so they're technically addresses in memory. And if the address contains a bad character, then we can't actually put it on, we can't actually overflow EIP with that address because the bad character is going to get changed. So what we do now, we can copy, well, actually, I can't copy those because obviously I can't copy between these machines, unfortunately. But what we can do is we can use this Mona jump command. I do have the string there, so that's going to be useful. So I'm going to say Mona JMP for jump. We want to jump into the register ESP. And then in later versions of Mona, so previous versions of Mona used to be -B for the bad chars, but now it's -C PB, and then you put the string of bad chars. So if we click into there, we should get another window. I think it's this one, maybe. Nope. Oh, it's the log window, isn't it? Hang on. Yep, log data. So in the log data window, which is window 2, you'll see that it's it says it's right. So it's looking for an address that basically is equivalent to jump ESP. So it could be a jump ESP address. You can also use call ESP. There's a few others it searches for. These are all jump ESPs, but specifically it filters out these bad characters, right? And so we found a total of 9. We can use any of these. So let's use this one. So 625011AF. So I'm just going to write it here. 62. Actually, that's not how you do comments in Python. 625011AF, I think it was. Let me just double check. 5011AF. Okay, and this is in big endian format, and 32-bit buffer overflows like this are little endians, so you just have to write it in reverse every 2. So effectively we're going to do AF, then 11, then 50, then 62. And that's simply just because that's how it's written onto the stack. It's kind of weird, but you can read up on it. It makes sense if you understand what's going on. Okay, and we can leave that here because this is a comment. But what we're going to do is we're going to remove the payload because we don't need that anymore. And I guess what we could do, again, to be thorough, is we could recrash the app, but we could put a breakpoint in here. So I'm going to copy the address. We're going to open the app again. Oh, hang on. Yep, you are correct. Someone just pointed out in the comments, this isn't going to work because I need to put the X's in. I'm getting ahead of myself. Okay, yeah, so otherwise it would have actually written those ASCII values to EIP, and I would have probably stared at it for a while, wondering what was going on. So I've reopened it, I've started it, and I'm going to just jump to this address. And when we're doing this, we don't need the X's. So this is definitely a jump ESP. And I'm going to right click it, click breakpoint, and click toggle. And so effectively, whenever the EIP is loaded with this, it's actually just going to pause the application, and it's going to say it down here. So what we'll do is we'll just crash it again, and if I go back, we see, yep, breakpoint has been triggered. The pause, the program is paused now. So now we can just press play again, and it's going to error out because we haven't got anything in ESP yet. Okay, so you don't have to do that. It's just nice to know that the jump point works. But next, what we can do is generate a payload. And because this is Windows, we want to use a Windows payload. There's going to be shell_reverse_TCP. And remember to add the bad characters here. So I'm going to copy this. Actually, copy this command. I'm going to open. Yeah, actually, now I'm going to do this. So it was 07 to E and a 0. Now, the format we want is, you could use Python. I made it easier because I understand not many people understand like C code and everything. I tend to change this to C, and I'll show you why in a minute. The port will leave as 4444. The IP address, let me just double check my IP address is this. So I'm going to copy that and put that there. And then I think that's going to work. So if you generate the Python code, it technically creates a variable called buff, B-U-F. And then you get multiple lines where it's just appending to buff. However, this is technically Python compatible. You just need to copy everything from the first quote here. So don't copy this line. Copy from the first quote all the way down to this last quote. Do not copy the semicolon. Copy selection, and we're going to go into our exploit. And in the payload, what we're going to do is remove those quotes, do an open parentheses, paste, and then we're going to go down to here and do a close parentheses. And that's technically valid Python. So it just saves time for me. So that's all good. The other thing you want to do, because we used, because we had bad characters, we had to encode the payload. So the Shikataganai encoder was used. So when this payload decodes in memory, it's going to use up some space, and we don't really want it to overwrite any of the EIP. So what we're going to do is we're going to add 16 NOPs. So a NOP stands for no operation, and it's this byte x90. And all it does is when the CPU comes over a NOP command, it basically just moves on to the next one. So it's basically, they're called NOP slides. Effectively, it will just slide all the way down. Nothing will change. It's just basically almost telling the CPU, oh, skip to the next one. So what we're going to do is we're going to edit exploit.py again, and I'm going to put this into padding. So the NOP byte multiplied by 16. Mojo says NOP is actually move EAX, so EAX to EAX. So I guess it technically does nothing, but it actually does, you know, something on the register, but the effect is nothing, right? Correct me if I'm wrong, because like I said before, I am no way a master at this. All right, so we have everything set. I got the right port. So what I'm going to do is I'm going to start over here. Well, actually, I'm not. I'm gonna split my terminal, and let's increase it a bit. I'm going to listen on port 4444, and then hopefully, unless I've done something stupid, this should work. But I have to obviously reopen the program. And it's running, so python exploit.py. Hooray, it worked. So we get a shell back. Obviously running as the use that we were running the OSCP binary as. Okay. That's good. I was given the way this stream started, I was half expecting this just to not work at all. So I'm glad that did. That's pretty much it, though. That's the end of this. So that we went over Overflow 1. There are 9 more. They all have different offsets. They all have different bad characters. Some have more bad characters than others. Some have a few. So I definitely recommend, especially if buffer overflows are your weak point, to go over this. Hopefully the VPN at TryHackMe is going to work better for you. I still have no idea why it's not working very well for me. I honestly, it's just a recent thing. When I first started with TryHackMe, it was fine. Anyone who's watched my streams in the past know it's been fine. But yeah, so it's hopefully going to work better. I think honestly that was all I really was going to go over. We've got like 7 minutes left. I only scheduled this for an hour, so if you guys have any questions, I know I've seen the chat scrolling up in the other window. I haven't really been checking out the actual questions though, so maybe I should scroll up and see. Hopefully people are answering them in there. I'm just gonna quickly scroll down. If anyone has any questions, just ask them now, and I'll get to them in a minute. Why does the ifconfig change to red in your prompt? That's because it's invalid. Because apparently I have IPA now. That's the reason there. Lots of people talking about bug bounties. That's fun. Isn't there a Metasploit module to generate the shellcode for this thing? Yep, we used it. Could you also use Moan to do this? Find the offset. Yeah, I think a lot of people were like guessing ahead. So that's good. Why does it find the pattern 3 times? I can't remember. I think when we were using the find MSP, I'm not entirely sure. It might have been that it was actually finding it when it was in EDX and ECX. There were 2 other registers that were overwritten, remember, as well. So it might have been that. All right, I think I missed that the mayor was hosting me. Thank you. Thank you very much. Anyone wants to check out the mayor did a stream as well of this, but he went a completely different route, and I learned a lot from his stream because he used Wine to run the OSCP binary. So he actually downloaded it and did everything in Linux. So that was actually really interesting. So I would definitely check out his stream as well. I think it's still up on his Twitch. Okay, and yeah, I'm going to record this. So technically, Twitch records them, and I then export them from Twitch to YouTube. So I will, I'll do that, and I'll probably cut out the 5 minutes at the beginning where nothing was working. So only you guys will know. What do you do if you can't add 400 bytes? That's a good question. I don't really know a good answer to that because, again, I'm not very good at stack-based buffer overflows. All that I did here was stuff that you need to do for the exam, and I don't even pretend to be an expert in any of this. So I think there are, however, ways in which you can jump around the code. Jump around in memory, sorry. So I know that there's things, and there's a thing called an egg hunter. This is the only thing I know about stack-based buffer overflows that are more advanced than what I just did was egg hunters, because I technically coded one in the OSCP labs because I was trying to rewrite an exploit. So what an egg hunter is effectively you put the payload in the initial buffer overflow. So in those 1,978 bytes, you hide the payload somewhere in there, and then you put enough code after EIP that it searches for a specific string in memory, and when it finds it, it executes that memory. So that's why it's called an egg hunter. Technically, you have two payloads. The first has this egg, so it's usually like a 4-byte string. So I think I used OSCP. And then after that, you have the actual payload. And then the second part, which comes after EIP, is a very small amount of code that just searches for that string in memory. So that's what you do. There are definitely other tricks if you don't have enough space, but that's the only one that I know about and can explain at least to some degree. If I hadn't used the C option, how would the Python look? Let's do that. So let's just do Py. Yeah. So it looks like this, right? So you could technically do this. You just have to copy all of these, and then the only other thing you have to do is when you go into your exploit code, you can either paste them before the payload variable and then set payload equal to buff, BUF, or you could delete the payload variable completely, paste the buff variable, and then change payload to buff here. So you can do either of those that work as long as the payload bytes are getting into this buffer at some point. However, for me, this trick with the C one, I forget how I learned this or where I learned this, but it was so much easier because you just have to copy some lines and just surround it with parentheses. So, do you have any additional courses / rooms coming out related to OSCP prep? No, not really. Especially since I have no idea if I'm going to get into any more trouble with this one. But seriously, I don't know. Maybe I might do like a few OSCP like machines. Obviously not calling them that because those 4 characters are banned. But yeah, I might have a go at creating something. Are we expected to be able to do multi-stage stuff for the OSCP exam? The multi-stage, like the egg hunter, no. So the exam buffer overflow, without going into too much detail, if you've done the OSCP course and you've done the SL mail one from the course, you should be fine for the exam. Obviously, I can't tell you what it looks like or really anything about it because that violates their rules. But if you can do the SL mail and you can do all this, you can do this stuff, then you'll be fine. But yeah, and I would definitely say if you're taking more than an hour to do the buffer overflow, then you probably need to practice. Because even including screenshots, you can do this in less than an hour. I mean, I just streamed it, and the stream lasted about an hour while I was doing this, so that shows that it can be done, right? I think in the exam I think it was 38 minutes, and that includes screenshots. So obviously I was like under exam conditions, so I was stressed and just speed running it, but it's definitely doable. I know people have done it in like 20 minutes because they're very good at this stuff. So it's nothing to be scared of, but definitely if you're taking more than an hour to do it, you definitely need practice. Just trying to see if there's any more questions. OCP a bad Chaz. Do stack buffer overflow good? Should people still use this for prep? Yep, use anything. This box actually technically has... I'm scrolling up because I've forgotten which ones. It has the SL Mail installer, so you can install SL Mail. It has the BrainPan binary. It has do stack buffer overflow good, and it has the original Vuln server. So by no means was I trying to limit people just to using the one that we custom wrote. If you want to use any of these, you can. They all should work. I tested it, but there's just no tasks related to them. And the reason the SL Mail is an installer is because I think it's like a 30-day trial. So you kind of have to install it on the host itself, which is kind of annoying, but otherwise, I'm pretty sure going by the date, it would just get disabled in 30 days. But yeah, thanks for watching. I think I probably have to end the stream there. But I hope that was educational. As always, please follow me on Twitter. I've got a YouTube. The links should be on the screen at the bottom. Obviously, subscribe to my Twitch. I do have a Discord server as well, which I occasionally, chat to people in that. And generally speaking, you can message me on Discord as well directly. So yeah, thanks everyone for watching. And I will have this uploaded to YouTube at some point next week. But yeah, thanks guys.